Thanks very much. Hello, everyone. My name is Jeff Morris. I'm Vice President of Product and Solutions Marketing at Couchbase, and I'd like to welcome you. And today I want to talk about what's happening in the database market space right now and how it's been evolving. And it's been evolving very, very rapidly throughout the course of the last 18 months to 2 years. And what I want to characterize it as is the notion that the debate between using a relational database or a NoSQL database platform is really over. And what I want to explain today is the top 10 relational compatibility capabilities that a NoSQL platform needs to address or maintain in order to simplify the choices that a development team has in building out their applications. And I think it's really interesting right now in that what we're seeing in the marketplace is this transformation of user experience and this desire to build modern applications. And modern applications themselves, we see, are actually contain a vast amount of capabilities built within them. Number one, the goal, of course, is to deliver this great user experience. And typically that user experience needs to be highly personalized. So a personalized user experience oftentimes also involves a device. So it needs to be either mobile enabled or mobile device capable. And it needs to be able to run anywhere. And in many cases, these applications are designed to be global in nature. And in many cases also contextualized in any geography. So an application might run but present itself a little bit differently in Europe versus North America, for example. It needs to support real-time capabilities, like in terms of this highly personalized experience. It needs to be able to match the particular attributes of what a user wants to do or evaluate, and oftentimes needs to match that to a complex catalog of real-time information. And then it needs to support transactionality because many of these applications are indeed, they're operational in nature in that they do something, they persist and store data, but they also take advantage of real-time analytics at the same time. So these applications are indeed hybrid in nature, operational and analytic processing all at the same time. They need to deploy everywhere, as I mentioned. They need to support things like 5G. They need to support always-on availability, and they need to be flexible and cost-effective in terms of how you deploy them, where you deploy them, and what cloud you put them in. And ultimately, for those who are actually building these kinds of applications, you need to support high degrees of efficiency. I was talking to a customer the other day who was talking about building a microservices-based application that's powered by data inside of Couchbase, and they're doing 130 releases a day to these microservices. So they're delivering very, very rapidly on their deployment, and so it needs to support that kind of efficiency very, very readily. It needs to also take advantage of skills that these developers might happen to have, like knowledge of SQL, for example, of course, and then ultimately try to avoid, I think, what we might characterize as one of the early burdens of this century was the notion of building polyglot persistent kinds of architectures, those that incorporated many types of databases, each of which had a particular core capability or core competency to it, and weave them together in this sprawling mass of data processing capabilities so that you could deliver these kinds of features to a user who's on the go. So what we really hear when I break down those kinds of requirements for what this modern application looks like is, we see the problems that customers are facing because of them are things like the database that they're using today, oftentimes relational, is failing in terms of its ability to perform at scale. And oftentimes because it's got such a structured, rigid schema, it's not flexible to change and it's not easily adaptable. And of course, if the last year and a half taught us anything, it's that applications need to be agile and adaptable and be flexible very rapidly based on what perhaps your users are doing. Maybe they're all running to curbside pickup, for example. It needs to deliver this incredible mobile experience, as I just mentioned, and it needs to continue to be cost effective, which oftentimes is code for it needs to be moved to the cloud, where resources are more abundant and much more flexible themselves, much more elastic themselves, and to keep overall operating costs down. So what we oftentimes see is this the journey that a customer goes through here is first to fix the database or prop up the database itself using an in-memory caching system, and to just simply improve performance right away, perhaps between the user community and the database itself, and then incorporate those personalization attributes now that you actually have them cached, that characterize the human objects that you might have in your system, the account profiles or user profiles that might be in the system, and finally begin to take advantage of your transactionality that's in your application and build something that is much more operational in nature. So that's sort of the journey that we see customers going on. But now I want to end up talking about what really are these key requirements that that these customers are going to both expect and and need as they move through that journey. So here we go. Our first 5 sets of requirements I'm going to summarize very, very quickly, but then I'll dig a little deeper into some of the attributes here. Number 1, they need data model flexibility. And this is oftentimes driven from the perspective of a document database, like MongoDB, like DynamoDB, or Couchbase, that allows for editing and manipulation of a JSON document as its storage structure, that affords the developer the ability to adjust what data is getting stored in real time on the fly while the application's running. You can't do that typically in relational-based systems. You have to go ask the DBA for permission to add a column or add add new schema structures. Not so. You get this schema flexibility with JSON, and that really the most obvious place where that happens is when you are dealing with a user profile and you discover while the application is running, there's particular attributes about a user, like Jeff likes red shirts, and you might want to store, color preference for shirts, and within my profile. You could do that in a JSON-based data system because you can write directly to that data structure and add that field directly. So that's a big, big advantage, and one of the that second driver as to why customers go and look for alternatives to relational systems, is because they need that flexibility. But the second one is continue to support operational processing. And here, it's carry over the traditions of a relational data store with all the dependability, all the transactional reliability built into and trust built into the system, and other capabilities like user-defined functions, like global secondary indexes and the like, and schema structures, so that you can actually share your designs with somebody else and maintain your institutional knowledge, how the data structures were developed and designed, and then how they could be carried forward. So that operational processing and structure is really important here. Third is addressing that performance issue. Ideally, you want the database itself to operate in an in-memory manner, support in-memory processing, because that is the fastest real-time processing you're going to have available to you. And oftentimes, this is illustrated in key-value store type databases like Redis or others that really support sub-millisecond response times when they're processing data, and then make it persistent as it's as is necessary to keep the data around. Next would be support search capabilities in some kind of form, because there's a number of applications that require document type search or location based search that is not readily easily done in a structured query language or a heavily indexed type language or system. So search is really key here. And finally is analytic processing, because we know that there's going to be, and there is becoming this necessity for analytic and AI capabilities, processing capabilities, the brains of the application, to not only evaluate what's available in real time, but then also to carry over what's and feed back to the application the results or the analysis, the results of a model run within the application. So all of that needs to be supported in the same platform. And of course, oftentimes analytic processing takes up a huge amount of horsepower. We've talked all the time about the separation between compute and storage capabilities on the analytics side, but there's also a balance that's required of being able to support both the operations and not interrupt those while doing the analysis at the same time. Ideally, without any ETL data transfer or a data pipeline kind of movement of the data, because that just creates more sprawl, and that's one of the things we're trying to avoid. So those are my first five, really quickly, and I want to dig a little deeper into some of them. So this dynamic, flexible data organization, it's basically how would I go about mapping a traditional relational schema into a new format like a document and JSON document structures. And there's a number of strategies for doing this. And there's a number of really cool benefits of doing this as well, where we were all taught in our youth that you had to normalize your data into a variety of different forms to minimize the amount of data that gets stored and minimize the amount of duplication of the data that gets stored. In modern times, disk space is actually much more affordable, and and it's easier for us to lay out a larger data object and think in terms of objects as to what is it that you're trying to process. And you might get a little bit of data duplication, but that's okay. And you might want to nest a data element inside a document, and that's okay. And then you might also want to support things like arrays inside the document, and that's okay. But that is still being able to support this schema-like shapes of the system is one of these primary requirements. So what we end up suggesting is this notion of scopes and collections. There's NoSQL structures have things like collections or buckets or documents, as I mentioned. But there is a logical mapping that we can take that maps in Couchbase parlance. I call a database a bucket. That's the largest container that we have inside of our own NoSQL system. And then the next layer down, I have scopes, and the next layer down from that, I have collections, which is essentially types of documents and groups of documents, and then the documents themselves. So this is really kind of the logical structure that we take on inside of a NoSQL system. But at the same time, you notice that it maps directly to what a schema design would look like, where a bucket looks like it could be a database. The scopes are the equivalent of a schema in relational terms. The collections are your tables. The documents are your rows in the tables, and then even the key value in the document or the arrays in the document are the cells in your table. So that logical mapping is really helpful in us being able to make portable data from your old system into a new one, and that's really key. And ultimately, this notion of being able to disperse data in these structures like collections gives us a lot of advantages. Some of the advantages are it makes repartitioning the data itself very, very easy, and rebalancing. If I want to continuously rebalance my database, I can do that. And and at the collection level, that happens really easily. And the cool thing is you can probably even have your indexes, which can be mapped to the collections as well. Those can be replicated alongside or sharded alongside and rebalanced alongside the data collections that they are indeed indexing. So a lot of flexibility in there. And what's really cool is when you start to think about collection level processing, rather than the full database processing, right? You can imagine the performance advantages you're going to see in that kind of design, where it's a smaller data set that you're dealing with, smaller indexes that you're dealing with, and each of these are going to be much faster than your traditional models might end up being. And ultimately, this maps really cleanly, as I mentioned earlier, to a microservices-based architecture, which is also one of the new modern development best practices that's evolving. So that structure is number one. The second thing I want to talk about, though, is let's tap into the existing knowledge of your development team. Everyone knows SQL. And what's key here is, especially when I'm trying to support transactionality inside of the system, because we need that operational processing. That was one of our requirements. You really want the developer themselves to not to have to change context in terms of how they might define a transaction. What you really want is SQL compatibility, and serving the same kind of structures in a NoSQL system as you would in a relational. So I've got my relational transaction, a simple one up top, a little bit more a complex transaction with save points and rollbacks on the bottom, but fundamentally they're the same, right? It's same syntax, same same instructions, and very, very simple for a developer who knows SQL to become familiar and succeed in a NoSQL based environment. So in the transactional use cases, these are everywhere, right? They could be shopping carts, they could be inventory updates, they could be payments, they could be confirmations, they could be real-time offers, they could be bookmarks in your media stream. So that the application of this kind of this capability within a NoSQL system is really one of those core requirements of, if we're going to get out of that rigidity of our relational system, we need to be able to move forward and support this kind of transactionality in the new one. So let's talk a little bit about performance now. And one of these core requirements is in-memory processing. And how many of these, there's very few relational databases right now that are designed in a memory-first architecture, right? Because they're just, the memory was much more expensive and much smaller than what is available today. But in the case of our environment, you get in-memory streaming of all data coming in and out. You get an in-memory cache of that data that you're processing and is getting worked over and over again. We have ephemeral or memory-only buckets. So if you only want to have transient data come through, you can design it for that. That could be things like PII data or healthcare data that you don't want to have persistent. You just want it to be processed and then forgotten. And then you can also have memory indexes be in memory only as well. And the structure of all of this is such that each one of these different services that I'm describing, a data service, a global index service, a query service, a search service, each one of those can be assigned to to operate on a particular node in a cluster. And of course, we want a clustered architecture for availability, as well as performance. So when we look at a singular database that has those kinds of services and structures inside of them, right? It's got that in-memory caching capability. It's got that JSON flexibility. It's got that relational structure and SQL familiarity. It's got the search capabilities. It's got data streaming capabilities. It's got high volume analytic processing capabilities and enterprise level security. Those are the expectations we have. And and doing this inside of a single data store has an immense amount of benefit here, in that you don't have to deploy a polyglot persistent kind of architecture that takes that depends on the strengths of each one of these different types of databases. You can use that from a single data structure. And we're going to see that become more and more popular as data consolidation really becomes necessary, and information sharing amongst applications, divergent applications, becomes much, much more popular. So this multi-model kind of support is one of those key capabilities, and to support all these different types of workloads. So when we deploy these services, though, one of the real benefits of a cloud-based deployment or a distributed deployment is I want to be able to performance match the requirements of my application to the data, to the database, to the infrastructure that it's running on. And here I can do that. We call this workload isolation, or multidimensional scaling. And what it allows us to do is take any one of those services and allocate them to particular nodes in the in the cluster environment, and make sure that each node itself is configured to cater exactly to the performance specs of that service. So you can optimize, especially think about cloud kinds of deployments. What you really want in a cloud deployment is to redline every single EC2 instance that you happen to be deploying. You want that to be going at full speed to optimize or maximize your spend in the cloud. And this kind of capability allows you to do that. So this deploy, isolate your workloads is one of these requirements that's key to maintaining both high performance and cost effectiveness in cloud-based deployments. Of course, we know, as I mentioned earlier, these applications are going to be global in nature. So you need a distributed architecture that supports things like cross data center replication. And location filtering, so that the residentially for data sovereignty purposes, data that needs to live in the EU lives in the EU and it stays there, whereas data that's in North America can be stored in North American environments. But the replication that needs to happen of data that's common to both, easy peasy. And then there's also that last core requirement is number 8 here, is support for edge and mobile. Now this gets really, really interesting because we have some very, very difficult and different types of problems that we're all familiar with. Connectivity. Your network goes down all the time, or is intermittent all the time when your cell phone moves from tower to tower, for example. But what you want is your data center to be aware of what you're operating at the edge and in mobile. You want synchronization that is indeed hierarchical, so that any time that you do have available network connectivity, the data can come back and be reacclimated into your active cluster. But we also want an offline first kind of design, so that any device can be synchronizing data to any one of its peer devices, as long as it's got some kind of a network connection, like Bluetooth. You can peer-to-peer sync between a tablet and a phone, and then when the phone leaves that environment where there's no connectivity, it syncs all the data back to the main environment. That's a really key requirement for these very highly mobile, highly transient kinds of applications that we're seeing start to pop up. So getting down to number 9 and number 10 are actually strategies for how deploy as a database as a service, because it's going to be your most cost-effective means of deployment. So you want fully managed capabilities here. You want comprehensive monitoring and support. You want the option for support of a hosted solution that where your database provider runs all the infrastructure for you for convenience. But then you also might want the control of running in your own virtual private cloud. And you can do that in both cases. And then if you are indeed experts in cloud and you want to manage your environments yourselves, you want that flexibility too. So you want the option of having self-managed capabilities. Oftentimes that introduces Kubernetes-based support and management capabilities. So you're looking for those kinds of features and requirements in your system, and all the way down to supporting hybrid, your old on-premises environment as you like. So we look at these as requirements number 9 and 10. But then let's kind of wrap how we see this kind of playing out. And as I mentioned, the debate part being over, relational versus non-relational, relational versus NoSQL. Really what you want is the strengths of relational and that flexibility and performance of NoSQL fused together. And that's what we're talking about, right? So the things that you trust and are familiar, like your schema, like your query language, your SQL query language, like transactions in the query language, user-defined functions, cost-based optimization, those kinds of capabilities are what we have always expected traditionally out of relational databases. So you want that carryover. And then you also want that editability of a JSON document. You want the performance of in-memory processing. You want the multi-model capabilities so that if I need to do inverted index based full text search, I can do that. If I want to do hourly backups out of the system, I can have a service that does that and runs all the time. And if I need it to support my development stack, right? As many SDKs as are popular right now in the programming space. Those are much of the flexibility capabilities. And then, as I mentioned, just is all of those deployment kinds of capabilities. Put it wherever it needs to go, in your cloud, in a public cloud, in multiple clouds, cross cloud. All of those capabilities want to be supported. So if I was looking at how I might migrate a system, this is just really just to give you a sense of what it is. Oftentimes, there's that balance between the level of effort it takes to do a migration and the risk of something going wrong while I'm doing it. So, the high degree of effort would be, let's rewrite it and skip everything. We're not going to migrate any data. It's going to take a long time, higher degree of risk. You could say, I'm going to redesign the schema, right? And keep your business logic, keep your application capabilities intact, but follow NoSQL best practices. You could do that. You could go refactor everything. But if I switch this around and start to say, what's the easiest thing for me to do right now? Well, just host the data, right? Take your schema out of your relational system and put it in the NoSQL system. That was what I showed you right in the beginning with that scopes, collections, bucket, schema-like design idea. Then I can start to optimize for JSON efficiency as I'm starting to get familiar with the NoSQL system. Then I can refactor the application and start to make sure that my services that are using the data are indeed becoming more and more efficient. Then I can redesign my schema on the fly, and then I don't have to rewrite the application. Right, that's kind of the migration philosophy that we're taking on, and we've got a number of both professional services offerings and strategies for doing this. So if you go to Couchbase.com, you can see videos on how we're migrating MySQL systems into Couchbase, et cetera, very, very easily. So when you really look at some of those advantages, right, these core 10 things that we're talking about, that flexibility, right? Relational databases don't really support that. That structure on demand as necessary. Relational systems certainly have the structure, but it's not very dynamic or flexible. You want your declarative or your SQL query language, right? Because that's what everybody knows. You want ACID transactions. You want sub-millisecond response time. You want multi-purpose, multi-model capabilities. All of these are kind of how everything ends up playing out when you look at those core strengths of relational versus what you see in a typical NoSQL system and what you might see in a system like mine. So winding down, there's clearly a space for moving these kinds of applications forward, modernizing your existing applications, and getting out of that antiquated kind of environment, and getting out of the early 20th century kinds of designs of I'm going to do document and I'm going to do in memory and I'm going to do search all at the same time. Very, very inefficient. What you really want, and then you don't want to get vendor locked in in the cloud. So those are a lot of the other decision points that you're going to end up considering as you might move from relational to NoSQL. So for developers, it's all familiar. For architects, it's very, very performant. And for DevOps, it's really easy and cost effective. Those are really the core things I want everyone to remember out of this. And finally, I do want to do a quick plug for our conference, which is online and free as well. It's happening next week. It's called Couchbase Connect Online. You can register at connect.couchbase.com. And I thank everybody for your attention today. This has been a really fun event, and enjoy the rest of the show. So. Do I have an experience with OrientDB and what do I think of it? I do actually. I used to work for a graph database company, one of Orient's bigger competitors, and I like some of the notions that OrientDB has, like document structure of of graph structures. But I think really where it was, my knowledge is about 2 years old, but its core scaling capabilities were still a little bit immature, and the in-memory processing kind of capabilities that you might find with other graph systems like Neo4j, Tiger Graph, those kind of guys, really put Orient at a bit of a disadvantage, in terms of what it was trying to do. But I think overall a pretty clever design in terms of mixing in those different models themselves.